All right, good morning to everybody on Zoom and 2 people here. Any questions about substitution, SN2 substitution, anything? Hopefully you had a chance to grab the handout from Blackboard. And we're just gonna keep working through that, work through some examples. I sent the right videos Wednesday, so come on, install, man. Sorry. We're gonna crank up in 1 second. Let me just get the technology working.
Tell us what time we leave and tell us the day before, so we leave at one.
All right. Still can play. I like that. That shows me a lot. Shows a lot. All right. Any questions about the SN2? We're gonna work through some, we'll work through some examples, but I just want to make sure nobody had any questions about what we covered on Monday. If not, I'm gonna jump back in and I'm gonna leave this one to you. The second example, and we're gonna go ahead. Would y'all rather do, well, we know what it is. I'm gonna leave this one to you all. Right, all you, just to predict the product. You don't have to worry about all the rate law and all that stuff. But just predicting the product. All right, let's go to the SN1 reaction. Talk about. I can talk about. All right, so one of the major differences between SN2 and SN1 is seen right away, right? The substrate, which is here, right? That substrate is tertiary. So it's excellent for SN1. And the reason is because of how the SN1 reaction happens, how the mechanism happens, which we're going to talk about today. And then that tertiary substrate is going to make sense. It's going to make more sense. All right, so SN1 works on secondary or tertiary substrates. The solvent is protic, as opposed to the SN2, which is aprotic. Right, and this is the key is right here. It's stepwise and it has an intermediate. Always, if it's an SN1 mechanism, there always will be a carbocation intermediate. So stepwise and always forms a carbocation intermediate. So let's do this first. Let's go through our little labeling exercise. Leaving group, nucleophile, solvent, yada, yada, yada. And then after we do that, we're going to go into detail about the mechanism and the rate law and all that, just like we did with the SN2. So SN1 is substitution, right? Nucleophilic, unimolecular. What does that mean? Can somebody tell me what that, when I say unimolecular as opposed to bimolecular, what does that mean? What did bimolecular mean? Okay, two things where? Where are there two things in that mechanism that make it bimolecular? In the Good. So two things in the rate determining step, right? So unimolecular means what? That there's one thing in the rate determining step. So we're going to talk about that and talk about the rate law and the energy diagram, all that stuff. So where is, I've already labeled my substrate. Where's the leaving group in the substrate? Bromine. Good. Always the most electronegative atom or functional group in the substrate. That's my leaving group. All right, so what that means is that here I can think about this and keep in mind when we talk about any of these reactions, even going forward, the reactions that we're going to look at next in the next section, everything works on the same principle of nucleophile and electrophile, everything. If you can find the nucleophilic nucleophile and find the electrophilic site, it's gonna, that's how it works. Everything works on that principle. Where's the partial positive? And where's the partial negative? Right, everything. That's how every reaction works on that principle, unless it's radical. All right, so now that's my leaving group, and this is by default what? Nucleophile. See, it's negative, has electrons to give away. It's a lover of nuclei, so it's trying to give a pair of electrons to something that's positive. All right, and then over here is my solvent, methanol. It's protic, so that means it's going to be able to give up H plus. That OH proton has a pKa of about 16, so it can come off. It doesn't come off readily, but it can come off. All right, and if you remember the other day, we talked about protic and aprotic and how protic solvents slow down SN2 reactions. They actually speed up SN1 reactions. So write that down somewhere. Protic solvents facilitate SN1 reactions. Right? They don't slow them down, they help them go faster. And there's a reason. Everything has a reason, and we're going to talk about
And slow down SN2.
it. Yes. Slow down the SN2 reactions, and they facilitate SN1 reactions. All right, let's go through so we've identified all of our stuff. If you watch that ICE method video that I sent, it helps you to go through that process of identifying everything. Solvent, nucleophile, leaving group, substrate, all of that. What's the product? It's a substitution, right? So what happens in the substitution? So the leaving group is getting, okay, and then what's coming in? Okay, so the OCH3 group or the methoxy, we'll give this a name. The methoxy nucleophile is going to come in and replace the leaving group. Is that right? That's the overall outcome of a substitution. So it looks like the product is going to look like this. Plus what? ER minus. Is that right? Okay. Here's the difference in SN2 and SN1 right here. Let me show you why this can't be SN2. Here's my leaving group, and here's my nucleophile. All right. Anybody on that's zooming with us, anybody see a problem with that nucleophile trying to come from the backside like it did in the SN2? A whole bunch of carbons. I put all these decimals, you're not claustrophobic, right? I put all these desks around Michael. His desks have wheels, by the way. Right? I can't take those. But if I'm trying to get to Michael, y'all can't see me. You can see me, but you can't see the desk. Maybe I'll turn it around. So this is, Michael is the electrophile. I'm the nucleophile. I'm trying to get to him, but I got a problem because all this stuff is in the way, right? That's what's going on in this example. These methyl groups are shielding that partially positive carbon. This is where the reaction is going to take place. The methyl groups block that. We call that steric interference. This is why you will never do an SN2 reaction on a tertiary carbon. So steric interference or steric hindrance. Let's say hindrance. Steric hindrance. So SN2 on a tertiary carbon will never happen because of that. Because in the SN2 mechanism, the nucleophile always comes from the opposite side of the leaving group. And if the opposite side is blocked, it can't happen. Are y'all any questions about that? Everybody following that? Right, so SN2 will never happen on a tertiary carbon, ever, because of steric hindrance. All right, so let's talk about how it does happen, because it actually, this is a stepwise mechanism, right? And the first thing that happens all right, first thing that happens is the loss of the leaving group. Right, that's the first thing that happens. You lose your leaving group. This is the rate determining step. Also, leaving group is rate determinant. Nothing else. So how do I write the rate law for this reaction if the rate determining step only involves the substrate? Good. That's it. Mike said K times the concentration of the substrate for the reactants, and that's 100% correct. This is why it's unimolecular. So the rate law is going to be K times the concentration of the substrate. Right? Or any SN1 or any unimolecular reaction, it's going to be K times the substrate. Because E1 is the same way. All right. Questions? Any questions? The first step is rate determinant. And then in the second step, that's where you have the attack of your nucleophile. So the OCH3 is coming in here. Give me my product. All right. Any questions about that part? Every SN1 reaction goes through a carbocation. Right? Every SN1 reaction goes through a carbocation. You lose the leaving group first, you make a carbocation, and then the nucleophile attacks. So my rate law is K times the concentration of the substrate. And what do you think if I asked you to draw an energy diagram for this? What would it look like? Keep in mind there's more than one step. So what does that mean for the energy diagram? If one step is one hump, right? From reactants to products, you gotta have at least two humps, right, in a diagram. Good. So the energy diagram is gonna look something like this, right? So I'm gonna so the first step is rate determinant. So it's got to have a higher activation energy in the second step. I'm gonna put that in here. So this is going to be the intermediate. It's going to be the substrate. And then from intermediate, I'm going to have a lower activation energy. Intermediate product. So you go from substrate to intermediate, which is in the well, and then intermediate to product. Are y'all following? Anybody not see it? Substrate to intermediate, intermediate to product. That's what we call a stepwise mechanism. Right? What that means is what it says. The mechanism happens in multiple steps, or at least the rate determinant step has, well, let me not say that. The overall mechanism happens in multiple steps. But the substitution part, if it's a part of a larger mechanism, it's going to have two steps. Right? When we talked about the SN2, what type of mechanism was that? What did we say? Anybody remember? It's concerted. All happens at the same time. So it's concerted as opposed to stepwise. So those are your two types of mechanisms, concerted versus stepwise. All right. Can somebody tell me, look up the pKa of HBr and tell me if Br minus is a good leaving group? Because we can tell by looking at the pKa of the conjugate acid. So the conjugate acid of HBr or Br minus would be HBr. What's the pKa? -9.
Is it -9?
-9. Is that a good acid with a negative pKa? It's a great acid. The lower the pKa, the better the acid, right? Can we just do that? I know y'all already took the exam, so it's like negative, positive, I don't know. It's -9. -9 is excellent. That's a very low pKa. It's less than 0. So that's an excellent acid. That means that the conjugate base is also going to be excellent. So bromine is a great leaving group, right? Write this down. Good leaving groups speed up SN1 reactions. I'll try to highlight this. Excellent leaving group. Again, I have a chart in here somewhere. Here. I have a leaving group chart with the pKa's. So you can see bromine is near the top. Good, and you got fair to poor to bad, and then not leaving. And it's all predicated on the same concept of hierarchy, like the conjugate base concept. All right, let's talk about one other thing. More than one other. Let's talk about the solvent. I talked about that with SN2. We'll talk about it here. Right? When we did the SN2 reaction, What did the solvent do to the nucleophile if it was protein? Anybody? Surround you. Kind of like you go into a room full of people you know, and you see a person you know on the other side of the room, but 3 people come and talk to you and keep you from getting to the other side of the room. That's what it does, right? It just kind of calms you down, calms the nucleophile down. Hey man, how you doing? See you in a while. Yeah, yeah. And then boom, whole conversation. Meanwhile, the other person on the other side of the room is gone, right? You never get a chance to talk to them. So salvation can happen anywhere. It doesn't always necessarily, it's not endemic to SN2 mechanism. So right here, what do you think, if we got a protein solvent, what can it solve right here? I mean, if it solves the nucleophile, nobody cares, right? Because the nucleophile doesn't affect the rate. But what else can it solve besides the nucleophile? The leaving group. It can solve the leaving group and make it even more stable and more apt to leave. So let's think about that in terms of the transition state for the SN1, sorry. What do you think it looks like? Only for the rate determinant stuff, because this is going to have 2 transition states, but I don't care about the other. What does the transition state look like for the rate determinant step? Which is the loss of leaving group. I'm gonna draw that. What do you think? What's happening in the loss of leaving group? What bond am I breaking? The bond to the leaving group. So the transition state is just going to have, in this case, a partially broken bond between the leaving group and the carbon is attached. That's the transition state for that rate determinant step. Right? And so now you do this in a protic solvent. They're going to solvate that leaving group and relax it, make it more ready to use. I can put a bunch of protons up here. Those protons, same protons that can surround your nucleophile can also surround your leaving group. They'll solvate the leaving group and stabilize it. That's good for the reaction. All right. Any questions about that? And that will be this transition state right here. Call it TS1. Any questions about that part? So that's why this reaction works better in protic solvents. Because a protic solvent can stabilize your leaving group. What's the overall charge on the transition state here? If part of it is partially negative and part of it is partially positive, it's neutral, right? It's neutral. It's not like the SN2 transition state where it was negative overall. It's actually neutral. All right, questions about anything pertaining to SN1? But let's go back to one other question or one other thing. Can you see now why it works better on tertiary carbons? If the rate determining step is the formation of a carbocation, would you want it to be the most stable carbocation possible? Right, so tertiary is your most stable. So that's why it works better on tertiary. You can do SN1 on secondary carbons too, but that's going to depend on the solvent. If it's aprotic, it's going to be SN2. If it's protic, it'll be SN1. All right, questions about anything? All right, would y'all rather at this point work through some examples or do the E2 mechanism? All right, let's do that. I'm going to leave this one for you to finish, just predicting the product. Let's go to the handout. There's a handout back here in the back. Problem. Let's go to that. Actually, we're going to work. Let's work through 741. We're going to work through 741 and 741. And let's work through 750. Let's do those. And then we'll if we have time, I'll introduce E2, the E2 mechanism, and then we'll stop. All right, so for 741, it says for each pair, identify which will react more rapidly in an SN1 reaction. So what we're going to be comparing in each example is either the structure of the substrate, whether it's secondary, primary, tertiary, or allelic, and we're going to be comparing leaving groups. Because there's no solvent indicated. It's understood to be a protic solvent because it's telling us that it's SN1. So you look at that structure and leaving group. That's what you're comparing, structure or leaving group. Right, with the structure, what you're thinking about, you're thinking in terms of the carbocation that you're going to make when the leaving group leaves. If it's primary, you know, that's going to be a bad carbocation. So let's look at number one. A, I'm sorry, let's look at A. What do you think? You have a primary alkyl halide, the chlorine as the leaving group, and both. You have, over here, you have a tertiary alkyl halide. What do you think? Again, we're comparing the structure. Go ahead, Mike. Tertiary, right? What you're looking at with the structure is what would the carbocation look like. For this one, the carbocation will look like this. Over here, it's going to be on a primary carbon. That's terrible. Remember this CHEM for stability. Tertiary is the most stable. Methyl is the least stable. So before methyl is primary. So it's tertiary, secondary, primary, and then methyl. So if that's more unstable, then which one is going to be faster? It's going to be the tertiary, because that's going to give you the best intermediate, the more stable intermediate. All right, let's look at B. All right. What do you think? Same scenario. This one. Right, bromine, so it's the same leaving group in both. So you're comparing the structure. Again, this structure is primary, this structure is tertiary. So this one is going to be faster. It's going to give you a more stable intermediate. Right. Questions? What about C? What would before you answer that, let's look at what the carbocations look like for each one of those. So for C, one of your carbocations is going to look like this when chlorine leaves, and the other one looks like this when chlorine leaves. What's the difference between those two? Okay. All right. Thank you, Sade. I just saw your message. I can't see the chat, so if you have a comment, you got to unmute it and say it. But thank you. All right. You said one has a double bond and one doesn't. Okay. So this is an example. We've seen this before. Haven't we? When we did resonance, it's an allylic carbocation, allylic cation. So I can do resonance over here, and if I can do resonance, what does that mean for the stability of that cation? More stable. If I have a resonance form here, can I do resonance over here? Right. So my cation is now resonance stabilized. Already looking for any reason of discrepancy from an HPC. Everything's got to be perfect. Right? Resonance stabilized. That's good. So which one is faster? This one. We've seen that on the cation before. All right. What about D? D is same structure. They're both tertiary. What are we comparing to D? The leaving groups. So we need to look up the pKa for HCl, and then we need to look up the pKa for toxic acid. So let's go back to the chart. So we're going to put that here. Write this down that we're comparing leaving groups. Because the structures are identical. We're going to use the pKa of the conjugate acid. All right, what you got, Mike? I see with the chart already. What's the pKa for HCl? -7. HCl is -7.0. What about toxic acid? It's the third one down. Yeah. -0.6. OTS H. -0.6. Which one is the better acid? HCl? Yes. HCl has a lower pKa. That means it's a stronger acid. That means it has a more stable conjugate base. So up here, what we infer from this is that chlorine is a better leaving group, which you can see from the chart anyway, right? It's above the OTS. If you have that chart, this is OTS right here. So it's a tosylate. This is what OTS is. This is the O part, and the rest of it is toluene sulfate. only is it's called a tosylate. All right, let's do 742, because this is a good question, because it gives me a chance to talk about another aspect of SN2 and SN1, which is stereochemistry. All right, you see how the bromine is wedged in the star material coming out of the page? That's what that means. If it's on a wedge, it's coming out of the screen. And if it's on a dash, it's going back into the screen. Right? That's what you call chirality. This is a chiral center. Chiral center. If a substitution happens on a chiral center, if it's SN2, the chiral center gets reversed. Right? And doesn't that make sense? If the bromine is coming out of the page and the nucleophile is coming from behind it, right? And this is on a wedge. When the nucleophile comes in, it's going to be on the opposite side. So that chiral center, if the reaction is SN2, the chiral center gets inverted. In the product. Right, and you can see that. You can see that this is coming out of the screen, and that's going back into the screen. Also, DMSO is also another key to knowing that this is SN2, because this is a protein. Polar A protein. Actually, a very good A protein solvent. So all that said, this is an SN2 mechanism. The cyanide right here is my nucleophile. Right, and then of course bromine is my nucleophile. Always replaces the leaving group in a substitution. All right, so let's look at the questions. How would the rate be affected if the concentration of the alpha halide, which is the substrate, we double? What do you need to know in order to answer that question? The rate law. Right? We know it's SN2. So the rate law will be what? Rate is K times what? The substrate times the concentration of the nucleophile. Do it. All right. Anybody zooming, not see that or not following that? In order to know how the changing either one of the concentrations changes the reaction, you got to know the rate law. Right? And know that it's second order. That's what the 2 in SN2 means in biomolecular. So if I put it, if it says what happens if I double the concentration of the substrate. So let's just do that. Let's take these over here and let's just do that. I'll put a 2 here and a 1 here. So I don't change the nucleophile. What should happen to the rate? Should also double. Is that right? Anytime you change either one of those is going to affect the rate because it's bimolecular. All right, what about in B? How will the rate be affected if you double the concentration of sodium cyanide? So this is substrate, this is nucleophile. Wouldn't it also double there as well? What if you double them both? It will quadruple. Good. What if you triple them both? It'd be a nine-fold increase, right? And that's all those questions are asking is how we understand the rate law. But before you get to the rate law, you got to know what reaction is happening, if it's SN1 or SN2. All right, any questions from anybody on Zoom? No? Yes, maybe? All right, let's do the next one, and then we're done. Pre-homecoming celebration begins today. If we could do this in 2 minutes, you would start 2 minutes early. Never mind. All right, what kind of reaction is this? Is that a tertiary substrate or secondary or primary? Never mind the OH group. How many carbons are attached to where because the OH is your leaving group. It's bad, but it's still a leaving group. So what's the bond order there? Primary, secondary, tertiary. You're talking about this carbon right here. Tertiary carbon. Once you know that, you know what? It can't be SN2, right? Because the carbon is too crowded. So now we know it's SN1. Are y'all following? That's why it's so important to be able to identify your nucleophile, your leaving group, your substrate. And that helps you to answer the rest of the question. What will happen if you double the concentration of your alcohol, which is the substrate? What's the rate law for SN1? It's K times what? The substrate. Is that right? Nucleophile is not involved. It doesn't matter what happens with the nucleophile, it will not affect the rate. So what happens if I double the amount of alcohol? I put a 2 in there. So double the rate. What if I halve it? I cut it in half. The rate would decrease by 1/2. All right, next part of that question says, how would the rate be affected if the concentration of HBr is doubled? Is HBr a part of that rate law? So what's going to happen to the rate if I dump in more HBr in this reaction? Nothing, right? The rate will not change. Because if you look at the rate law, there's no term for HBr, so it doesn't change the rate. It can't change the rate. That's what when we say it was unimolecular, that's what this question is alluding to.
Okay.
Yeah. Rate won't change. Good. Get a minute back. Have a good weekend. Any questions online? 13 participants. What a shame.
Have a good day. Thank
All right, y'all take care.
you. Have a good day.
All right, you too.
Have a
Thank you.
good day.
Thank you. You too.